This is the first of two videos that work through a single example as a way of working out both the logic and the computations of analysis of variance. The situation that we're going to look at involves students in a school who were divided into three groups, and we're going to need the analysis of variance because our t-tests that we already know how to carry out can only compare two groups at a time, and often in situations such as this one, we have 3, 4, or even 5 groups. So the analysis of variance can cover more groups, and in fact, it can even cover situations with more than one independent variable, which we will be getting into next week. We need to have the analysis of variance because the tests we have so far, the 3 different kinds of t-test, can only compare 2 groups at a time, and yet often we have situations where there are 3 or more groups that need to be studied. There also are many situations, in fact, most of the research done in the modern world, in which we want to simultaneously compare the effect of more than one independent variable. In this course, we only touch our toes over the threshold of that kind of multivariate analysis, but we will do it next week when we look at a factorial or two-way analysis of variance. So we're laying the framework here for both of those reasons for doing the analysis of variance. The particular study situation that we're going to use as our example involved grade school children who were being tested in math. Before the students had even the first test, they were randomly assigned to one of 3 experimental groups. They, of course, did not know about it, and it's important that the random assignment happened first, so that there was no possibility of the teacher being biased and choosing better students for one group or worse students for another. After giving them the first math test, the teacher behaved differently with the members of the 3 different experimental groups. Grounding her action in some of Carol Dweck's theories about the growth mindset, she decided that she would see how praise affected the work of the children. The students who were in Group A got a tremendous amount of praise for their effort in studying and preparing for the exam. The students in Group B got moderate amounts of praise for their effort in studying for the exam. And Group C did not get any praise at all. They only received the information about their score on the first exam. All of this was the experimental treatment. The dependent variable was still to be measured. The next day, at the end of the math lesson, the teacher gave another test, and the scores for all the students were recorded, as well as the amount of praise that they had received for effort on the previous test the day before. The teacher and the researchers thought that the earlier praise might have an effect on the students' scores on the second test, and our ANOVA F ratio is going to be the statistic that lets us know whether that idea is supported or fails to be supported. Unlike our t-tests, where we could subtract the means and have subtraction as the basis of our analysis, once we have more than 2 groups, we're not able to subtract all of them from each other at once. So our F-test is going to be a ratio about the variance between the groups, which would be due to the treatment effect that defined those groups, and the variance within the groups, which is variability that is due to all the other random components, whether the students had a good night's sleep or a good breakfast, were their parents fighting at home, did somebody say something nice or unkind on the way into the classroom. All those random effects will be in the denominator in the variability within groups, while the numerator will have the impact of the praise variable. When that systematic component, the part that's due to praise, is large, we're going to say that the groups differ from each other, and in that situation, our F statistic will be greater than 1 and will tend to be saying that we have a significant difference. So we're ready to phrase our null and alternate hypotheses at least as narrative statements. Our null hypothesis says that students will have similar scores on the second math test regardless of the amount of praise they received. And our alternative hypothesis says groups who receive different amounts of praise will have different mean scores. Notice that neither of these statements implies a direction, even though we have an expectation that students with more praise will also probably score higher. Our hypothesis is stated in such a way that they could score either higher or lower than the students who received less praise. Here we're beginning to look at our actual numbers, and you see on the left the scores for Group A with a lot of praise, Group B with only moderate praise, and Group C that had no praise. And I've created a little graphic representation. There really is no horizontal axis here. I just spread out the scores from left to right so that we would be able to see them. And it lets us visually understand that the scores in Group C really do look quite a bit lower than the scores in Groups A and B. On the previous slide, I had computed the mean for all 18 of these scores. It was 4.611. And on this graph, I've drawn in a line that shows where that mean is for all of the scores. If you remember how we compute the variance, we look at the distance from any score to the mean, and I can represent those distances by drawing a line. This is the value that I would get if I were subtracting the mean from each of the scores. The scores that are below the mean would be negative scores. The scores that are above the mean, I'd get a positive deviation score. And if you remember from the information we had in week 2, overall, the sum of these deviations would add up to 0. So there's as much length or distance above the mean as there is below the mean. When we look at this graph, having drawn in those scores, we immediately notice that almost all the scores in Group A and most of the scores in Group B are above the mean, while every single score in Group C is below the mean. So we already begin to have a hint that there's some difference between the groups in that last test score based on the amount of praise that they received. On this slide, you can see that I've carried out over here on the left all of the computations for computing the variance. I had the scores. After I had the scores, I computed their mean. For each score, I computed its deviation. I squared those deviations, and when I added up all of those sums, I get a sum of squares. When I divide it by n minus 1, I in fact get my variance, which I might need in my write-up. But the thing that's most important for our analysis of variance is this sum of squares total computation. And we'll be dealing with that for the rest of our calculations. So we've already seen the variability overall in the data set around the grand mean of all of the cases taken together. But if we want to consider the impact of praise, we want to see if those groups have different means, and then we'll look at the variability within those groups. So our null hypothesis can be tightened up a little bit more. We can say that the amount of praise given has no impact on the math post-test. And over to the right, you can see that we've in fact phrased it as an equation. The null hypothesis says that the means in the population, in other words, if we did this procedure repeatedly for all students at this grade level, that the group means would be equal. However, you'll notice that we don't have a similar equation for the alternate hypothesis, which says that the means will be different. We are not going to hypothesize that each mean will be significantly different from every other mean. Instead, all we can hypothesize as an alternative is that at least some of the means will be different from each other. In this slide, I've carried out the work to compute the mean within each of the groups. So within group A, I found a mean of 6. In group B, 5.5, and group C, that one whose low scores we've already seen, we see as having a mean of 2.33. Let's look at the students' variability around the mean inside their group. So remember that inside the group, each student received the same amount of praise. All the students in group A got quite a bit of praise. All the students in group B got a moderate amount of praise. And when we get to the students in group C, that's the group that did not receive any praise whatsoever. All they received after the first test was the score that they had received on the test. So when we look at the three groups, we can see that even though they all had the same amount of praise, it does not mean that they all had the same score on the second exam. There is variability within the group, and that's the random variability that we spoke of before. Whether their mom gave them a kind word, or they had a great breakfast, or maybe the school bully crunched on them a little bit before they got to class. All those positive and negative factors create random variability within each group, so that even though they receive the same amount of praise, their scores are not identical. Using the same sort of process that we used to create the overall variance, for each one of these groups, I was able to take the group scores and the group mean, and for each student to subtract the mean of the group from their score and square it, so that I end up with a sum of squares for each of the three groups, and that sum of squares for each group represents the total amount of variability inside the group. So I'm seeing the most variability inside group A, the one that got the highest praise, and I'm seeing the least variability inside group C, the group that got no praise. And if we look at the picture with the lines drawn in, we can in fact see that there were a few people either very high or very low, above or below the mean in group A, but that in group C the scores are more tightly clustered around their mean. So this three numbers taken individually show me the amount of variability within each group. If I add those three numbers together, if I combine them, it's going to tell me across all 18 students what is the extent of random variability, the part that we know is not due to praise, because we computed these sums of squares within groups where every student received the same amount of praise. In analysis of variance, we call this the sum of squares within groups, and in this situation, we can see that when we add them together, we get the number 32.833. If you remember, we computed a total variability that was all the variability across all of the cases around their grand mean, and it was a lot bigger. It was over 80. So we can see that some of the variability is random, but there's also going to be some variability that is due to the treatment effect. So our goal in the analysis of variance, that word analysis, refers to partitioning or dividing things up. In this situation, we're going to be partitioning our total sums of squares into two parts. Some of it will be the systematic variability that occurs between the groups, and that's the variability that's related to the treatment, in this situation the level of praise. and the rest of the variability is the random variability within the groups due to all of the sorts of differences there might be among the students aside from the praise level. So we'll be taking our overall sums of squares and breaking it down into two different components, and we've already created the sums of squares within with the computations we've done already. While it is possible to compute the sum of squares between by another set of computations, it's actually much quicker to just use subtraction. We already know our sum of squares total, and we already know our sum of squares within. So if we subtract within from total, what's left over is going to be the between sums of squares. So I've just made use of the fact that total is made up of two parts, within and between. So when I know any two of these components, I'm automatically able to compute the other. If I know within and between, I can add them to get total. If I know total and either of the other two, by subtraction, I can obtain the value that I don't know already. So in this first part of learning the analysis of variance, we've managed to break our sum of squares, or our representation of variability, into two components. And we're going to say that if the between part, which is the systematic part due to the treatment, if that component is large relative to variability inside the treatment group, then we want to say that the treatment, in this situation praise from the teacher, had an effect. Our F statistic, which we will finish computing in the next video, is a ratio of these two components, but we have to adjust them for the sample size and for the number of groups. But because we have the systematic component on the top and the random component on the bottom, when we have a large value for F, it means we would have a large treatment effect relative to the random variability, and that will be the situation in which we reject our null hypothesis. In the second video, we'll show how we finish computing F and what its degrees of freedom look like. If there are any of the concepts in this first video that aren't clear, I encourage you to go back and re-watch those sections before you go on to the second video, because we will be making use of the same information that you've already had when we get there. As soon as you're ready, let's dig in for the second video.